Hello class, glad to have you back and sorry it's been so long to get this out to you. Today we're going to be focusing on the sums of infinite series, so let's dive right on in. In this setup here I have point A and point B, and these 2 points are 100 meters apart. Let's assume you're going to be at point A. Yes, this will be you in this example, and we'll have your friend here. Let's call him Phil. Phil will be point B away, well, which in this case is 100 meters. So you're being asked now to move halfway between you and Phil. And notice I've moved Phil. So if you're going to move halfway, this is actually a pretty simple problem. We can actually try to grab this point here and move it about halfway. Well, let's put a number to that. Halfway is going to be simply, let's put it in pink, 50 meters. Okay, not so bad. Part B, well, says it's the same thing. Move halfway between you and Phil. Alright. Not so bad. That would be just, what? Then since there's 50 meters left, you just went 50. Well, that's 50 meters left, so you need to go 25. Again, not bad. So we write 25 meters. Okay. Let's do part C. Move 1/2 the distance between you and Phil. In this case, it's going to be now 12.5 meters. I'm starting to see something here because I'm assuming part D, yeah, it's going to be the same. So in this case, we're actually doing it one more time. So if we do this again, you're going to get, what, 6.25 meters. And you can go on and go on and go on. But note that every single time we go half, okay, we go half here, and half here, and half here, we have this conundrum of never actually reaching Phil. Well, the exact point of Phil. So we always keep having it. Well, we have what we call, again, as you remember, a limit. So let's write mathematically what our journey is like, just without using these fun pictures. So we start by saying our first part of the journey was 1/2. Next part of the journey was 1/2 plus 1/4. The next part of the journey is going to be 1/2 plus 1/4 plus 1/8. And you should start seeing, well, a dot 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 progression. We rewrite this as 1/2, 3/4, 7/8. And if you note, as we keep going on, we should note this some pattern, and I'm going to rewrite this pattern as 2 to the n minus 1 over 2 to the n. In this case, 2 to the n refers to, in this case, that you're talking about the numerator and then you're subtracting 1. The same as the denominator, is just subtracting 1 from it. Well, if we take the limit of this, so I'm going to do this in blue, the limit as so we should note that there's a pattern between the numerator and the denominator, that the numerator is increasing by 1, the denominator is increasing by 1, and they're getting closer and closer. We've kind of seen this already as a limit. Well, we can see this pattern by saying that 2 to the n minus 1 over 2 to the n will fit the sum of any nth term. And if you wanted to try this out, you can just simply apply this formula here, to each one of these, and so on and so forth if you want to keep going. Try to get some of the more of these values. Now, I mentioned we saw this as a limit, so let's look at that. If we're going to do the limit, well, the limit of n approaching infinity for 2 to the n minus 1 over 2 to the n, you should note, is 1. As in that as you continuously add a half or take a half of your whatever distance over and over and over and over and over, you're going to have a total sum of 1. That's the most you can have in this infinite series. So this theorem I just wrote out, is referring to the sum of the infinite geometric series, and we're actually proving this in the last problem. So let me just walk you through and then we'll start applying this to some concepts. So this is saying that here your R, which is your common ratio, the absolute value of it is less than 1, and you have this infinite geometric series, so again you're multiplying by R squared now to the third term, R and so forth, and you get R raised to the n, that this whole thing converges to the sum of this theorem right here. So this is important, that's why I put in other colors. Now the important bit is this only exists for this system, so actually I'm going to underline that in another color to refer back to this theorem, and that if the common ratio is greater than or equal to 1 and the first term is not equal to 0, then the series diverges. So you have two different types. You have the convergence, I put this in red, convergence and divergence, the two different types. So let's look at this example. So in example 1 we have these terms here, 3 over 10 plus 3 over 100 plus 3 over 1,000 and so on and so forth. And we want to see whether or not this converges or diverges. So take a moment to pause the video and make an attempt using the information we have, which is right here. So first off, I'm going to look at what the ratio here is, and if you should note that you're increasing the denominator by 10 each and every time, so you have a multiplication factor of 1/10. So in this case, that's your common ratio. So let's compare that to our test here. If the absolute value of R is less than 1, it converges! Yay! And in this case, it definitely does, because that's definitely less than 1. So let's test that by placing it in the formula. I'm going to switch colors and say that our sum is now going to be equal to our first term, 3/10, divided by 1 minus 1/10. We're going to rewrite this, 3/10, and this is now going to be 9/10. Okay, I'm going to move this down. You're going to get this method, forgot to show that. So you're going to get 3 times 10 over 10 times 9, and you should note those cancel out. You're going to get 3/9, which reduces to 1/3. So you have a series convergence at 1/3. And notice that you've been using the sum of infinite geometric series for the longest time, or some infinite series, because this has been used before. 1/3 as a decimal has been used before. As a decimal, it looks like this: 0.33333333333333333. I kept writing. You can't see that, but this all equals to 1/3. Even this, writing any amount of frees is still going to be an approximation of the 1/3 value. So let's do one other one. So looking at this example, we should note that the ratio here is going to be 2. And in this case, we go back to our theorem and test to see, well, is this one less than 1, question mark? And the answer is no. So automatically, without doing any other work, you can say this series diverges. Remember, the difference between series and sequences is the series will have addition between each term. You're trying to find the sum of all the terms, not a list of the terms. And I think this is pretty noticeable if you actually note that as you add more and more and more, you're just getting larger and larger values. This is going to be infinity. There is no end to this. But in this case, we want to mention that the series diverges to infinity, not that there's a limit to infinity. Please note that difference. So for example 3, I want you to take a moment and pause the video, and there's going to be a part that actually quizzes you or asks you a question of what value you get. So take your time, try this one out. Alright, so let's work on this one together now. In this case, if you note, the ratio here is not some constant integer value, but in this case, it is a constant value of x minus 2. Well, we know that for the series to converge, r, absolute value r, must be less than 1. Well, since it must be less than 1, we're looking for some value of x that is going to make this condition true. So if we do plug in r for this value, we can test this out. And you're going to get that, remember, if you have an absolute value, you must consider when this statement could be positive and negative. So if we were to rewrite this, I'll do this in two different colors. So let's do this in blue. Let's consider the x minus 2 statement given. We're going to get x is less than 3. So in this case, we consider the other case of the negative being distributed to this whole system. And we're going to get negative x plus 2 less than 1. I'm going to minus 2. You get negative 1. And now, if I divide, you're going to get x is greater than 1. So now we have some interval here. And this interval here is going to be between 1 and 3. So that when x is in this interval between 1 and 3, this series will converge. Yay! And so we have a solution for this one. Alrighty. Hope you enjoyed this lesson, and I look forward to seeing you guys next time. Have a good night.